All right, let's pick back up where we left off. So we're talking about binary search trees, and I have given you an idea of what removal looks like. There's going to be 3 cases, and 2 of those cases made some sense. Like if you just had a leave to get rid of, just immediately just set that parent pointer, the parent's right pointer or the left pointer, to null. Now it's gone after you delete the node, of course. If you have one child, you can just move your child, or if you have one child, you can move that child back up to the original node that you're deleting, make it be that parent's position. Oh no. Boop. And in the 2 children case, who in the world knows what to do? Some fancy, smart people figured this out, and either predecessor or successor will fix this. And it's interesting to discover why. And so I'm going to give you essentially the algorithm for removal today, but I'm not going to code it up. So this is going to be your challenge for your lab. Okay, so for the leaf case, again, let me draw out my favorite tree as usual. And for the leaf case, it's not too bad. So once you've found the node you need to delete, and notice that it's a leaf, so assume you have a pointer always. Let's call that node n. Oh my. N. Let's call it n that we're about to delete. So let's pretend we want to get rid of the 3 perhaps. Okay, I'm going to call this 3 n. Okay, so we want to get rid of n. Well, obviously we're eventually going to need to call delete on it to delete the actual memory for that node. But how do we make the tree forget about it? Well, we just have to worry about this parent's left pointer. Make the parent forget this node ever existed, which is really sad. It's its child. We're making him or her forget about their child. So you need to figure out first if it was the left child or the right child. And you can compare pointers, of course. You can be like, all right, is the left pointer of the parent this node that I'm deleting? Or is it the right pointer of this parent, the node that I'm trying to delete? In this case, we'll notice that it's the left. We need to get rid of this left pointer and set it to null. Okay, so set the left-right pointer of the parent to null. And then all you have to do is remember to actually delete the node. So you're going to be calling delete, that is. So that's the idea. You have, you got to go to the parent, figure out if it was the left or the right child that you're deleting, and set their child pointer for the correct side to null, and then you can finally delete the node since you don't need it anymore. Okay, so that's the leaf case. Let's do the one child case. This one's a bit more involved, but it's still not too bad. So again, let's pretend we're let's delete 4. That's the node n we want to delete, and we need to figure out that it has one child. So somehow you figured out that it has one child. Maybe comparing the left and the right pointers and noticing that only one was null. To know that you're out of leaf, you notice that both pointers were null, right? So you know that you've got one null pointer, which is almost as good. So the idea is you have only one child to worry about. And it needs to move up the tree. In fact, its entire subtree needs to move up the tree. So maybe this is 2.5. We have a 2.5 node, and we have a 3.5 node. That would go in that spot, right? Less than 4, greater than 3, 3.5. Yeah, let's pretend we have these 2 nodes as well. This entire subtree needs to move up now. Okay, so the idea is you've got your beautiful subtree rooted here at this 3 node, and we need to get it up the tree. So it needs to become the new right child of 2. So you find this node's parent, again figure out which child of its parent it was, which side of the parent n was on. So we notice that here's the parent. It's the right side for the 4 node that we're about to delete. So we figured out that it was on the right side. And now it's our job to move its one subtree up the tree. And it's still valid to put it there, actually. You can see how if you replace the 4, like get rid of that, just make it one long right pointer, this is still a correct tree. It's got a 3, that's all this stuff is greater than 2. It's all still less than 5, of course. So you can move this right up there. Okay? So you're moving subtrees now. Move the entire subtree, which really just means move the pointer to this first node, that's the root of that subtree. Move the entire subtree to where, to the side of the parent that n was on. So for example, here you'll say 2's right child is now 3. And that will move the entire subtree because 3 has a left and a right child, and that's how you get further down the tree. And then you need to say that that child's parent was the old parent. So let's call this child. So make child's parent n's parent. Okay, so we need to put a parent relationship now, just like we put a child relationship in. Make child's parent n's parent, because we're getting rid of n. What was n's parent is now the child's parent. We're moving it up the tree to where n used to go. Moving its whole subtree. And so in this case we're saying 3's parent is 2. Okay, so remember that there's 2 sides of this. There's the parent's child, and then there's the new child's parent after we delete that one node. And this is super nice because we can just get rid of n and just make a really long right pointer in this case. Okay, so hopefully that makes sense. Let's go through it one more time. So the child needs to move up. This 3 needs to go right here. It needs to be the new right child of 2. And so we're going to find the parent, figure out which side of the parent the node that we're deleting is on, and then we're going to move the entire subtree, the one that wasn't null, so this one, up to where that node was. Okay, so we're going to make it 2's right child. We're going to make this, we're going to make 3 2's right child. Okay, and then we're also going to set the parent pointer for 3 as well. Okay, making child's parent n's parent. So we're moving the child to where n was in the tree. So for this example, 3's parent is now 2, just like 2's right child is now 3. Okay, so that's how we moved an entire subtree. And now you can finally delete n. Boop. So if that wasn't enough, you had 2 children. And you couldn't just replace one. If it has 2, you can't just like, all right, I'm going to take the right child and make that where I used to be. It doesn't really work like that because you have 2 separate trees at that point. So let's pretend that n is 5. We're deleting the root, in fact. Boop. So if n has 2 children, you can't just replace it with one of its children, because now suddenly you have 2 trees. Can't really do much with that. Okay, so we want to get rid of n now. N is the root of the tree. It could be 2. We could also be trying to get rid of 2. It also has 2 children. Same argument for this. Okay, so this is where the predecessor or the successor comes into play. I'm going to use the successor because we talked about that one in most detail. You'll be using the predecessor, I think, in your lab. Okay, so the key idea now is that you know in the 2 children case that the predecessor or the successor always exists because you have 2 children. So, key idea. N's, don't need that bold anymore, N's predecessor slash successor, oops, predecessor slash successor always exists. Because you can either go right and then left forever for the predecessor, so here's the predecessor, or you can go left and then right forever until you find, oh gosh, I'm so sorry. This is the successor, this is the predecessor, by going right and then left and then right forever. I get my directions mixed up sometimes. Okay, so predecessor, successor, and it always exists because you have 2 children. It always exists. And it's always one of the 2 previous cases. And that node is always either a leaf or has 1 child. What do you know? This successor, it's a leaf. Left and then right forever. There's no children. What do you know? This predecessor has 1 child. Oh man. Okay, this is where it gets fun. This is what you do. These are the easy removal cases. Are you ready for the trick now? So, swap the, I'm going to talk about the successor here. So, you can easily replace this with predecessor. Swap the, swap n's key with the successor's key slash value. So now, we just got rid of, we're kind of swapping those around. So now it's no longer 5 and high, it's 7 and hello. Now it's no longer, you don't technically have to move this one down, but it makes sense. This one's now 5 and high. You don't really have to copy that one, but just for symmetricity, I guess. You swap it, and then you delete the successor node. Okay, so that is the trick. You swap the node's key and value that you're trying to delete with the successor's key and value that you're trying to keep. So this one moves up the tree, this one, the old one moves down, and then you delete the successor. Oops. If we didn't have enough colors, here's one more. And you finally delete the successor, which now holds the 5, which was the key and value that we were trying to delete. And now it's gone. And this can be a recursive thing, because you can just call remove from remove. Because you know you're going to hit a base case, which is one of these two. Okay? In the two-child case, you're going to have to swap and then delete again. Delete for real that time. Okay? And that is the trickiest part. Okay? The idea is we found that we could use either the predecessor or the successor, and those are the easy cases to delete. So we're going to swap the node that we're trying to delete with one of those. You can pick either one, so I picked the successor. And then I can easily delete this node. Or I could have easily deleted this node by either just removing it from its parent or like moving the tree up. All right? Please yell at me about that if that didn't make sense. Hopefully the book also explains it, but this is the trick. This is why it works. This is why it makes sense. The only last thing, the only last piece of the puzzle is that you need to watch out for the case where you're deleting the root, because usually your tree is going to have the root saved in it, right? So, dun dun dun. Most often, like if you were trying to delete the root here, you would swap things out, but maybe your tree looked like this. It had one node in it. Okay, so here's a tree where you would end up deleting the root if you deleted the key 15, or alternatively, like if this was your tree, you're still about to delete this node, but you're moving this one up, right? You're kind of moving that one up. So whenever you do that, whenever you make something a root again, or get rid of the root, you need to change the tree, because it's like class tree, right? And it's saving somewhere a pointer to the root. You need to update that. You need to update that to be now the 16 node, or to now be null. So here, root should change to null. And then deleting 15 here should change the root to 16, the 16 node. Okay, so that's your last case, and this could happen, I guess, in either of the other two cases, right? In the two children case, there's going to be a swap, so I think that's okay. But that, in a nutshell, is removal, okay? And you're going to understand it very thoroughly by implementing it. And so let's talk about the running time complexity now. So for a few of these cases, it's quite easy, right? So let's talk about each case. So the leaf case, single child case, and the two children case. All right, so for the leaf case, we're just going up to the parent, removing a thing, setting a pointer, and then calling delete. So that's 3 lines of code or so. That is constant. Okay, just a few lines of code to move some pointers around. Single child case is exactly the same thing. You are, well, changing this parent pointer, or changing this child pointer, sorry, changing this parent pointer, and then deleting a node. Okay, so still just a few lines of code. Constant for the same reason. The two children case is where it gets interesting. So first you have to find successor / predecessor. And we know how long that takes. That's O of H. For the height of the tree, if it's a very long, long tree, it's going to take a while. Then, after you've found the successor / predecessor, swap stuff, which is just a few lines of code again, O of 1. And then finally, delete the successor / predecessor. Which is going to hit one of these cases, which we've just figured out is constant. So for the 2 children case, you just add all these together. So total, h plus 2-ish or so, O of h. Okay, for the 2 children case. So the worst case, it's the 2 children case. So in the worst case, it's O of h. But also, the way that I'm going to ask you to implement it in your lab, it's actually always going to be O of h, because usually you'll search first for the node you want to delete. And search, of course, we remember, takes O of h time. Okay, so add this to, I guess, either of these 3 cases, you're still going to get O of h plus O of 1, it's O of h, same, O of h plus O of h, that's just 2h now, so it's still, in the worst case, always going to be O of h. Okay, so usually you're going to want to search for the node, like I want to delete the key 4, so you're going to search for 4 first, which could take O of h time. Okay, so that is the running time complexity of removal. The space complexity of removal is actually super simple to talk about. For the leaf case, you're saving n. Maybe you're saving the key value as well that you're trying to delete. Maybe it was 3. And that's just a few, that's just 2 variables, right? 2 variables or so. And you've also got the function call. So it's really not too bad, because maybe for main you have to say, all right, I want to remove something. So you're going to save space in the stack for removal. And then you have the key that you want to delete, and then maybe the pointer, p, that you want to also, or n, the pointer to n, that you find based on searching for that key. Okay, so you just save a few pointers, really. It is constant space to remove. I guess technically it could be negative space because you're getting rid of stuff, right? In the worst case, it's the 2 children case, and you're calling remove twice. If it's the 2 children case, you're also going to call remove. Again, I guess you could use the same key, and then you're going to find the node where it is now, things like that. You can make that a bit smarter, but you're only going to ever have 2 calls to remove on the stack at a single time, because this second call is always a base case. It's always the case that it was one of the easy stuff, the leaf case or the 1 child case in that removal call. Okay, so no matter what, you're just saving a few pointers, and in the worst case, it's like 2 and maybe some ints. So like 4 variables or so, who knows? So it's still constant. So that's the space complexity of removal, and that is everything. That's all you need to know to implement a binary search tree. Congratulations. So with that, I want to show you how C++ does it. There are 2 STL ASTs, or not ASTs, sorry, ADTs. So in the standard library, they implement a set and a map using a special kind of binary search tree. You're reading about them in your book. They're called RedBlack Trees, but you're never going to implement those in this class. That's an upper division algorithms class. That's the lab for that class. Okay, so that's going to be a while in your career. You'll have to wait, but it's still interesting. And let's talk about what a set is, and we're also going to look around in the documentation. So a set is when you just hold a bunch of stuff. So a set is when you hold a bunch of stuff. You just want to know whether or not you have it. So you just want to look and see if the thing that you put into the set exists. Like, you can put stuff in, delete things. Check if you have something. And this is stored as a binary search tree where you just care about the keys. There's no values. The keys are the values. The keys are the values. So I make a set of things I want to keep track of, like, all right, I have 42, then I also added 12, then I also added 55. This is now just a binary search tree with nothing but keys inside. So if I wanted to know, hey, does my set currently have 12, I'll just search for it. Okay, the keys are the values. And so my best example of that is going to be for Pokemon. So your Pokemon card collection, of course, can be represented as a set. Do you have this card or do you not have this card? So I have conveniently made your lab revolve around this idea, so I apologize in advance if you hate Pokemon. But let's go to the documentation now. So let's go back here. So a set, you can read about it, it's fun. Really, this is the first thing that you only need to worry about. It's a set of a certain type, set of elements of a certain type. So let's look at the constructor. Here's how you use a set. So you can make it start empty, you can make it hold initially some values, and you can iterate through them. You can see if things are there. So insert, erase, find, count. Count should ever only be 1 or 0, right? Things like that. So put stuff in, see if you had them. So it's like a purse or a wallet or something. You have you can put stuff in and you can retrieve it and see if it was there, see if you brought it. Okay, so Pokemon example. Let me make an example with sets. So, if I did this right, I have copied into today's folder bst.h, which is from your next lab. So, coming at you from the future, I guess. Oops. There we go. And here is the struct Pokemon that we will use to store things. Dun, dun, dun. Now, how do I want to do this? I forget most of the numbers, so we might just have to make them up as we go unless I can figure out what they are. So we're going to copy this into a new file, stl examples.cpp, let's say. Paste that, and then let's put this up here. I guess I don't need that anymore. So that's what a Pokemon is. And so now let's make a set of all the cards we have. Okay? So okay, so you can start out empty. And we can add them one by one. Okay, so the first thing we can do is add them one by one. Let's go to the docs and we can say insert element. So we can just give it the value itself and it will insert. So we can say insert 20, insert, I don't know, Charmander. Let's do this. So Charmander looks like this. He is number 4. His name is Charmander. And his type is fire, of course. And also we need strings, I guess. Okay, that's a simple example. Let me try and compile this quickly. Of course not. So we're going to get some errors, so let's look at them in detail, if I can compile it properly. Let's go to the first one. There are so many. Boop, boop, boop. Let's see here. What does it want? What is the problem here? Aha! You see that? What it's pointing to? It's pointing to a less than symbol. Oh, shoot. It needs the order of things. Okay? It's a binary search tree. So it needs to know how to order our stuff. We need to tell it when it's less than, when two Pokemon are less than each other, or when one's less than another. So we'll say bool operator less than. We'll give it a way to do that. Constant Pokemon 1, constant Pokemon B. You need to be able to order Pokemon. And C++ does that with a less than function. Alright, so when is a Pokemon less than another? Well, we'll use their number. All Pokemon are numbered, if you were not aware. So we'll say return a dot number. Is that less than b dot number? If that's true or false, that will determine whether or not the whole Pokemon was less than. Alright, let's see if it's happy. That's all I needed. Okay, so now we can insert more things, of course. Let's do the 3 starters. Bulbasaur, and then we're gonna do Squirtle, of course. His number is 7, and he is water type, of course. How could I forget? Alright, so now we've got 3 Pokemon in our set, and we can check and see if they're there. So we can, I guess it's hard because we have to remember all the information about them, but let's go to the docs and see how we can check and see if they're there. So find or count will work. So let's see count. Is it there? Do I have it? And this is what it is good for. So we can say cout count. Hey, was Squirtle in our set? And it should tell us, yes, there's one thing. One thing called Squirtle. I have them in my set of Pokemon cards. Okay. We can also search for another that doesn't exist. $25, if I remember correctly. Yeah, Pikachu, and he's electric. We do not have a Pikachu in our set, so that's a 0. There's nothing there. Count 0 for Pikachus. Alright, get us back there for the next slide. You can also iterate through a set, and because you're iterating through BST, it's going to give you ordered things. Because the underlying set is a BST, it'll give you back stuff in order. So you can iterate through the whole thing using iterators. And we can get ranges even if we wanted to. It's all up to you. So if you want to start somewhere and then go from there, you can find a Pokemon to get an iterator to that element, to get an iterator to that Pokemon, and then starting at that Pokemon, you could go in order by advancing the iterator. Okay? So technically, if you wanted to. Oops. By using .find, it gives you back an iterator. Then you can advance it as far as you want. Alright, so I'm just going to go through the whole thing, because why not? So we'll say for set of Pokemon iterator it equals our Pokemon cards dot begin. It is unequal to our Pokemon cards dot end it plus plus or plus plus it. Then we'll say cout it number space it name space it type new line. Okay, so a lot going on there. But as you know, of course, we can change all of this to just be super simple because we're using C++17. For each Pokemon, constant Pokemon reference or constant auto reference if you wanted to, P, you can say P.number. So instead of IT slash, we can delete everything, like say P dot, okay? Oh, I'm so sorry. Gotta get rid of the arrow as well. That was not the thing that I wanted to do. There we go. Oh, oops. What have I done wrong here? Oh, yeah. For every Pokemon in the set. Excuse me. And again, it'll go in order. 1, then 4, then 7. Okay. That's the set. And map now is essentially the same, except values are a thing. So now you store values separately. So instead of at index 42, index 16, you held just the key 42. It's usually drawn like this, right? Instead of just the key 55, now you hold stuff there, okay? You say, hi, mom, or something, exclamation point. Now the values are separate from the keys, okay? So it's just like a hash table in a sense. So it's called map. It's essentially the same as unordered map, but it's, ordered. So what that means is when you iterate through it, you can use it just like a hash table, but you don't need to ever write a hash function because it doesn't use those. Just a less than. And the iterators, again, will go in order of keys. And so that I don't forget, I should talk about the complexity of these things. Okay, so just quickly, let's talk about that. Let's go through those docs briefly. And so instead of set containers map, it's essentially the exact same as insert, find, count, at, things like that. In place, we'll probably tend to want to use that instead of insert because we're cool like that. And yeah, that's essentially the idea. So we'll use in place to insert at a certain key, a certain value. All right, let's do that. We'll say, let's give ourselves some space now. Let's make a map of kind of Pokemon again. Map of int to Pokemon. So we'll take it there, number to Pokemon. Okay, so start out empty, and then we're going to insert using in place instead. Okay, so I think I will use insert here for fancy C++ reasons. So we're going to say number to Pokemon dot insert, and then the way you use insert is you use here's the insert method. You have to give it a pair of key and value. So there's a thing called standard pair. It takes the key type and the value type in that order, and then you give it stuff. Okay, so that's what it looks like. You give it the key, then the value, and I think in C++ 17 you actually have to give those hints to the types. So we should be able to say, in theory, actually should be able to just copy this stuff. Mostly. We'll say insert, we'll say the standard pair of the name, or the number, comma, and then the actual thing. Okay, so now it's 1, now it's 7, and then we also need to close that off. Okay, does it want the type really? Yeah, I guess it does. So it's int Pokemon. Okay. And of course it's called number to Pokemon now. I think that might work. If it compiles, I'm happy. Okay, we're good. And now we can go into stuff and be like, hey, what is number to Pokemon dot at, I don't know, 4, right? What's its name? And that should be Charmander. Yay. So it's getting it out, and then we can also iterate through it. But this time, it's not P for Pokemon, it's P for pair. Because it gets you back the key and the value, okay? So, number to Pokemon. P is a standard pair, and it has P dot first and a P dot second. Key is first, value is second. So if I want all this stuff, I have to say P dot second dot type. I have to say P dot second dot name, P dot second dot number. I can also print the actual key as well. P comma space, perhaps. P dot first. So this is going to print the key, which was the 1, the 4, the 7, and then also the value. I'll print it out like that. Okay. That, in a nutshell, is map. So we've talked about map iterators. When you iterate, you get a pair back. So you have to break that down into P dot first and P dot second. First is key, second is the value. Okay, so just keep that in mind when you're iterating. And I think this should tell me how to do it, begin and things like that. Yeah, so begin to end, you get back pairs of things, first and second. Okay, so finally, let's talk about the complexity of sets and maps. So they're BSTs, so they have the complexity of BSTs. But they're fancier. Because they're RedBlack trees, they're balanced. This means that O of H becomes O of log base 2 of n. Okay? Which is really nice. Not as sweet for maps because it's not O of 1 like a hash table, but it's still pretty good. But it has its trade-offs, like you're storing things in order now. So in the last few minutes, let me just prove to you why if you have a balanced BST, you get logarithmic time. And I am sorry for all the math that I'm about to show you. So if the tree is balanced, that means it's not too wobbly. And the intuitive way of saying that is like, it doesn't look like this. Okay, that's not a balanced tree. It would be nice, though, if it were like this. It was complete or even perfect. So that's a balanced tree. Okay, it's not leaning to one side or another. Okay, so what does that tell us about h is the next question, and I'm telling you that h is on the order of log base 2 of n if the tree is balanced. So you only have to go down log base 2 steps to find anything in the worst case. Okay, so to prove that it's big theta, like you can't do better and you can't do worse than log base 2 of n if it's balanced, I need to show you that this expression is an upper bound and a lower bound. So let's do that quickly. So when the tree is complete, not necessarily perfect, but it's complete, so it's got stuff filled in like this. Maybe it's missing this one still. When it's complete, let me draw one more row just to make it work. So it's always the case that here is 1, 2, 3, 4, 5, 6, 7. 7 nodes. So n is greater than 7. It's greater than or equal to 8 for this example. And what is h but 2 to the 3? Oh man, or sorry, what is n but 2 to the 3? It's greater than or equal to 2 to the 3, which is equal to 2 to the h. Okay, so this is true in the general case. 2, 4, 8, and it's greater than that because it's got more down here. So this is not something I'm going to test you on. This is just for your own information. And it's greater than or equal to 2h, which means, if you put it this way, h is less than or equal to log base 2 of n once you take the log of both sides. Okay, so log base 2 of n is an upper bound for h, which means h is O of log base 2 of n. So that's the one side, that's the easy side. The lower bound proof sucks. So let's pretend again we had our nice tree. Could be filled in, not necessarily filled in. Like it could be missing these last 3, for example. When it's complete, or even, like this is the worst case, it's complete, right? So when it's complete, the n, I'd rather keep it like this. Not necessarily perfect. The number of nodes is less than or equal to 2h plus 1 minus 1. So how many nodes could this tree have at most? Well, if it had those last 3, it would have had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, which is, what's h? 2 to the 3 is 8, 2 to the 4 is 16, minus 1 equals 15. That's the max number of nodes, okay? So it's always less than that if it's complete. It's exactly equal to that if it's perfect. So n is always less than or equal to 2 to the h plus 1 if it's perfect, or if it's complete, minus 1. Okay, so we're trying to make this an upper bound now. So we can put the log base 2 over here. Dun, dun, dun. So we bounded it. Let's take logs of both sides now, after we move the 1 over. Boop. Now we've got the log base 2 on this side. We're going to try and make it a lower bound. So it just so happens that this, log base 2 of n plus 1 minus 1, well, that's lower bounded by this. Just get rid of the plus 1, which itself is lower bounded by this if you pick an appropriate k. If you remember the definition of big omega, I can pick a k. I think 2 is fine, 1 is not good enough. And now I have a function of log base 2 of n that is a lower bound for my h. So I found that lower bound. H is big omega of log base 2 of n. When you have big omega and big O, it equals big theta. So we found that it's exactly always going to be log base 2 of n in the worst case, in the best case for balanced. It's an upper and lower bound, which is fun to think about. And so that's why you want your trees to be balanced. You can't do any better than a perfectly balanced tree. Okay? You can't get better than log base 2 of n in terms of running time for all this stuff, like search is now. So what does this mean? Search, insert, remove, etc. are all O of log base 2 of n. It's essentially binary search speeds, and you remember how fast that was. So that's my story. That's where I'm going to leave you here. So that is binary search trees. You are now masters of them. For some final exercises, if you're feeling up for it, I encourage you to change your removal method once you do this BST lab that's about to be released this week. Change your removal method to use successor instead of predecessor, because I think that's the one I'm forcing you to use. That's right. Use successor. Why not? And then for a hard challenge, try implementing those AVL trees that you're reading about in your book. That will make things a whole lot easier when you get to an upper division class and you have to go and implement RedBlack trees or something along those lines. You might even have to implement AVL trees, so you'll just have that done. Feel free to talk to me about it. It's all very beautiful and very mathy, as we've seen, but that is binary search trees. That's all I want to say, I guess. So I'll see you in your lab now.